Hey guys, welcome to this video on the 2019 Level 3 Mechanics paper. So question 1 is rollerblading. Ali and Chris are rollerblading. Assuming friction is negligible, the system of Ali and Chris can be considered an isolated system in the horizontal direction. Question A. State a relevant physical quantity that is conserved during a collision between Chris and Ali. So Chris and Ali are moving in a horizontal direction. When they collide, linear momentum will be conserved, assuming that there are no external forces acting. Because we assume that friction is negligible, we can assume that there are no other external forces acting, so therefore the linear momentum between Chris and Ali will be conserved. So for this question, we're going to answer linear. It's important to say linear momentum because in level 3 you also study rotational momentum, so it's important that you have to specify which momentum you're talking about. So linear momentum, and that's assuming no external forces acting. No external forces acting. And once again, I don't have the answer schedules with me, so I don't know what each question is actually worth. So I'm just gonna give a rough estimate of what each question is. So I'm not 100% sure, but I'm just gonna go off what previous papers have been like and put that into consideration. So this question is just stating linear momentum. So I think this is just a one-off achieved question. Question B. At one instant, Ali stops and Chris collides with her. They move off at right angles to each other as shown in the diagram below. Show that Ali's speed after the collision is 1.71 meters per second. Alright, so for this question, we're going to be assuming conservation of momentum. So the momentum of Chris and Ali before they collide will be equal to the momentum of Chris and Ali after they collide. So the momentum before the collision just would be the momentum of Chris plus the momentum of Ali. The momentum of Chris is equal to his mass times his velocity. So therefore, the momentum of Chris is equal to his mass, which is 60 kilograms, multiplied by 1.8. And that gives a momentum of 108 kilograms meters per second. And this momentum is acting in the right direction, so right. The momentum of Ali is also equal to her mass times her velocity. However, Ali is stationary, which also means that the momentum of Ali would also be 0. So momentum of Ali would be mass times velocity, which equals to 50 times of 0, which equals to 0 kilograms meters per second. Alright, so our initial momentum therefore equals to 108 kilograms meters per second to the right. So that also means that the final momentum will also be equal to 108 kilogram meters per second to the right, because we're assuming the conservation of momentum. So our final momentum is also equal to 108 kilograms meters per second to the right. So after the collision, Chris and Ali move off in separate directions. However, the vector sum of their momentum is still going to be equal to 108 kilograms meters per second. So we can draw up a vector diagram, and conveniently it is a right angle between Chris and Ali. So we can use the Pythagoras Theorem in order to figure out what Ali's momentum is, and then use Ali's momentum to find out Ali's speed. So if we draw up our vector diagram, our vector diagram. So we're going to have one arrow to the right, which is going to be representative of our final momentum, which is 108 kilograms meters per second. And we're going to have vectors for Chris and Ali respective to their directions. So we're going to have Chris's momentum somewhere there, and we're also going to have Ali's momentum, which completes the triangle. And we know that this angle here will be 90 degrees. We also know that after the collision that Chris moves off at 1.1 meters per second, and we can use this 1.1 meters per second in order to calculate Chris's final momentum. So Chris's final momentum would be 1.1 times of 60. So 1.1 times of 60, which is 66 kilograms meters per second. And we have Ali's momentum, which we don't know. We'll just say Ali's momentum is P for now. So as you can see here, we can now use Pythagoras Theorem and use vector addition in order to find out our Ali's momentum, okay? So our Pythagoras Theorem is a squared plus b squared equals to c squared. In this case, our c would be at 108 kilograms meters per second, as it is the final momentum or the hypotenuse. Our a and our b would be our momentum of Ali and our momentum of Chris. So 66 squared plus of p squared we don't know would be equal to 108 squared. So therefore, if we rearrange the equation, we'll get 108 squared minus 66 squared is equal to p squared. So therefore, our momentum of Ali works out to be 85.49 kilograms meters per second. However, we still need to work out Ali's speed. We have Ali's mass and we have Ali's momentum, so we can follow one more step of calculation to find Ali's speed. So we can say the speed of Ali is equal to 85.49 divided by Ali's mass, which was 50 kilograms. So 85.49 divided by 50. And that gives us a velocity of 1.71 meters per second, and that is rounded to our 3SF. Alright, and that would be your final answer for this question. And this question is either a merit or excellence level question. I'm not too sure which. I'm leaning towards merit level question for this one. So if you get your final answer of 1.71 meters per second, that will get you a merit grade. To get an achieved grade, I'm thinking if you can get up to drawing the vector diagram as well as setting up an equation, so probably somewhere around here, that could get you an achieved. Alright, question C. To save himself from falling, Chris sees a horizontal bar and grabs it. He then swings on the bar in a vertical circle. Chris's motion can be simplified by analyzing the motion of his center of mass, which is 0.7 meters from the bar. Assume the effects of friction are negligible. So question C. Calculate the minimum speed Chris's center of mass would have to be at the top of the vertical circle in order to swing up and over the bar, assuming he continues in circular path. So Chris's velocity will be acting tangential to the center of the circle, so it's going to be 90 degrees, so that would be his velocity, and his center of mass is represented by this blue circle. Alright, so in order to work out the speed, we need the centripetal force, which is the force on Chris's arms in this case. So at the top of the circle, vertical circle, so Chris is going to be up in the air. So we're going to have both the weight force, which is acting downwards, as well as the tension force of his arms in order to add up to get to our centripetal force. The reason they add together is because the centripetal force and the tension force are both acting downwards, which means that the net centripetal force will be the sum of both the weight force, which is acting downwards, and the tension force, which is also acting downwards. However, at the minimum speed, assumes that the tension force of his arms would be 0 newtons, and the only centripetal force would be equal to the weight force of Chris. Any less force than that, then Chris would collapse and be unable to move in a circular motion. So that would be the minimum speed Chris will have to move. So for this question, we can say that the centripetal force is equal to the weight force of Chris. And this is when Chris moves at minimum speed. So our force of gravity would be equal to the mass of Chris times gravitational constant. So F of G equals 2. Chris is how much was Chris again? Chris was 60 kilograms, so F of G will be equal to 60 times 9.81. 9.81, which is equal to 588.6 newtons. So we also know that this force of gravity is equal to the centripetal force, and the centripetal force is modeled with mv squared over r. And we can plug in our numbers for Fc. We know Chris's mass and we know the radius, so we can substitute these numbers in to find the minimum velocity. So 588.6 is equal to 60 v squared divided by the radius, which was 0.7 meters. So therefore, 588.6 times 0.7 divided by 60 square root would give us our velocity. And that gives us a velocity of 2.62 meters per second. So that's our minimum, velocity. So if Chris travels any slower than 2.62 meters per second, then he would collapse and be unable to move in a circular motion. Question D. Describe and explain the size and direction of the tension and weight forces at the bottom and the top positions, assuming Chris swings over at the top at minimum speed. Include force labels on the diagram below to support your answer. Alright, so at the top, we just mentioned this in the last question. So at the top, our centripetal force is going to be equal to the weight force of Chris plus the tension force of his arms. However, the question tells us that Chris swings at the top at minimum speed, which means that the tension force on his arms would be 0 newtons. So that means the only centripetal force would be the Chris's weight force. So at the top here, we will only have the weight force as our centripetal force. So we can say that this would be the weight force of Chris, and that acts downwards towards the center of the circle, which makes up our centripetal force. However, at the bottom of the circle, we still have our weight force of Chris, and that is still acting in the same direction, which is downwards. However, this means that in this case, when we're at the bottom, there has to be a tension force which counteracts the weight force of Chris, because the centripetal force always has to act towards the center of the circle. Or if there's not sufficient centripetal force, then Chris will just fall down. So in this case, it's going to be a tension force, a very large tension force. And this tension force is going to counteract the force of gravity, which is acting in the opposite direction in order to give sufficient amount of centripetal force to continue moving in a circle. So at the top here, we have our weight force, and that works together with the tension force. However, at the bottom, our tension force and our weight force are acting in opposite directions, so they are opposing each other. So at the bottom, our tension force is going to be extremely big, and that's going to counteract the force of gravity. So at the bottom here, we're going to have our F tension and our weight force, which remains the same. Weight force of Chris. Alright, so include force labels, okay, yeah. Alright, so now we're going to write out our answer. So describe, so at the top, in his arms, as well as the weight force. So both. Okay, however, no tension force in its arms, hence the FC at top is equal to Chris's weight force. Alright, we can say at the bottom of the circle, the bottom of the circular motion would be better probably. The bottom of the circular. Apologies guys, we just got cut off there. The screen recorder decided just to cut off there, so we're just going to continue from where we were. So at the bottom of the circular motion, we're going to talk about the weight force of Chris acting in the opposite direction of the tension force. So at the bottom of the circular motion, the tension force acts upwards into the center of the circle. However, the weight force of Chris acts in the opposite direction, which is downwards in this case. So this means that there is a large tension force to counteract the F of G, and hence sufficient centripetal force sufficient centripetal force to continue circular motion. So just to recap, so we have at the top of the motion, the centripetal force is made of the tension force in its arms as well as the weight force of Chris. They both act downwards, so hence they will add up and they both act towards the center of the circle because the centripetal force always acts towards the center of the circle. However, Chris is moving at the minimum speed, meaning that there is no tension force in his arms. That means that all of the centripetal force is made out, so it's equal to Chris's weight force. At the bottom of the circular motion, the tension force acts upwards into the center of the circle. However, the weight force of Chris will be acting in the opposite direction, which is downwards. This means that there is a large tension force in order to counteract the force of gravity, and hence, because there's a large tension force, there will be a sufficient amount of centripetal force to continue the circular motion. And that would be your answer for this question. And this question should be an excellence level question. So if you get all the way up to this bottom here, you'll get an excellence. In terms of getting a merit, okay, so let's talk about getting an achieved. So getting an achieved is however as Chris is moving, so perhaps just up to here could get you an achieved. For merit, I think you have to talk about at least one, so either the top or the bottom might get you a merit. So however, so you can say either from here to here could get you a merit, or from here to here could get you a merit. So from this much could get you a merit, or this much could get you a merit. Alright, thank you for watching this video for question 1. I will be posting questions 2 and question 3 later sometime, as I do not have time right now. Hope you enjoyed watching this video. If you did, please drop me a like. And if you have any comments, please leave it down in the comments below. And I see you in the next one.